The different schemes of quantization which we have studied so far fall in the category of what is known as scalar quantization. In scalar quantization, the samples are quantized independent of other samples. There is another category of quantization which is known as vector quantization. In vector quantization, a group of samples are quantized together. Now, a vector quantizer will provide a lower mean squared quantization noise compared to the scalar quantizer for the same number of average bits used to represent a sample. But implementation of vector quantizer is more complex than the scalar quantizer. The reason for better performance of vector quantizer compared to a scalar quantizer is that vector quantizer exploits the statistical properties of the samples which are being quantized. To be more specific, it exploits correlation among the samples to be quantized. There is a form of scalar quantization which also exploits correlation among the samples to be quantized, and that scheme is known as differential encoding. Let us look at the motivation for this differential encoding. For any quantizer, the quantization noise is directly related to the quantization interval, and this quantization interval is directly related to the dynamic range of the input for the given number of quantization levels. Now, for a uniform PDF, the dynamic range will affect the variance. So, the quantization noise is directly related to the variance of the input to the quantizer. This is the basic philosophy which is used in differential encoding. So, in many sources of interest, the sampled source output, which we will represent as xn, n denotes the time index. This sampled source output does not change a great deal from one sample to the next. What this means that both the dynamic range and the variance of the sequence of the differences defined as follows: are significantly smaller than that of the source output sequence itself. Furthermore, for correlated sources, the distribution of this differences, that is D, is highly peaked at 0. To understand this in a better way, let us take one example. Let us say I have source output which I denote by xn. So, this xn denotes both the sequence and also a sample of that sequence depending on the contacts. Let us assume these are the values which are being generated by this source. Now, if you compute the difference of the sequence obtained by taking the difference as current sample minus the previous sample, the sequence which we will generate is 6.2. I presume that x0 is known. In this case, we will assume it to be 0 without loss of generality. Then I take the difference between this sample and the previous sample. So, this comes out to be 3.5. Similarly, this sample and this turns out to be 3.5. This would be minus 7.3, 2.1, minus 0.6, minus 3.2 and minus 2.4. Now, given this different sequence, we can see that it is possible for me to reconstruct back in the lossless manner my original sequence by taking the current sample from this different sequence and adding to the previous reconstructed value of the sample. So, in this case it is simple. So, reconstruction will give me, so I start, this will be 6.2 itself because the initial value is 0. Then I take this sample, different sample, and add it to the previous value which I have reconstructed. So, this comes out to be 9.7. This 3.5 gets added to 9.7, so 13.2. This gets added to 13.2, yeah. So, this is 5.9, this gets added to this, so 8.0, this will get added to this, so I will get 7.4, 4.2 and 1.8. So, what I get is the perfect reconstruction, but there is little flaw in the argument that in practical scenarios when I want to transmit this different sequence, I will not be able to transmit with infinite precision. We are using digital transmission. So, what I will have to do is that I will have to quantize this different sequence. So, let us assume a 7 level uniform quantizer, and I presume that my reconstruction levels are -6, -4, -2, 0, 2, 4, 6. Using this reconstruction level, let us try to see what is going to happen to the different signal when I transmit. So, the different signal which I am going to transmit now is going to be quantized, and that value will be 6.2, this will be equal to 6, this will be equal to 4, this will be equal to 4, this would be equal to -6, this would be equal to 2, this would be equal to 0, this would be equal to -4 and this would be equal to -2. Now, what I do at the receiver is basically I follow the same strategy of reconstruction, take my error signal or difference signal. So, at any particular instant I will take the difference sample and add it to the previously reconstructed value. So, if I do this, I get my reconstruction, I denote that reconstruction as xq. It is not going to be the same as xn, you will see very soon. So, the first case is going to be 6, then I take this and add it to this, so it becomes 10. Next addition of this 14, this gets added to this, so 8, 10, 10, 6 and 2. Now, let us calculate the error which I am going to get between this sequence and the original sequence. correct. So, if I calculate the error, I have here 0.2, the difference between this and this. So, 9.67 minus 10 is minus 0.3, this is 0.08, minus 2.1, minus 2, minus 2.6, minus 1.8 and minus 2.2. Something interesting thing has happened. Initially I find that the error terms are quite low, but as I keep on progressing, the error keeps on building up, correct. So, let us try to understand this process little more in depth and see what is happening exactly. So, in our case now, what is really happening is something like this. We have an xn sequence and we obtain the difference sequence by taking the difference between the current value of the sample and the previous value of the sample, which is denoted by this block. So, this z minus 1 denotes the delay of 1 unit. So, I get my dn, then I pass it through a quantizer and I get my quantized value of the difference. So, this is what happens at the transmitting end, correct. Now, at the receiving end, what I am doing is that I take my difference sequence and to that sequence I add the previous reconstructed value, correct. And how do I get the reconstructed value at any particular instant is the difference sample, to that I add the previous reconstructed value, I get this. So, I delay this, I get this point, okay. So, what is happening is that I am getting my dn is equal to xn minus x of n minus 1, and this dn is passing through a quantizer to give me dqn, and I model this process of quantization as additive noise. So, in that case my dn plus qn, which is a quantization noise, this should be equal to dqn. Okay. Now, let us look at the first difference sample which I generate is a d1, which is equal to x1 minus x0. As I have said earlier, x0 is known at the receiver, we can assume also to be 0, it is not going to make any difference. So, this d1 is going to pass through the quantizer to get me dq, which is nothing but the original value plus the quantization error. Now, at the receiver I am going to reconstruct my x1, which I denote by xq. This would be equal to my previous reconstructed value, in this case is x0, it could be 0, does not make a difference, and the first difference sample. This I can rewrite it as now this plus this is equal to x1. So, the first reconstructed value has suffered the quantization error q1. Let us take the second difference sample in this sequence, which would be equal to so your dq would be equal to the reconstructed sample at the receiver would be equal to the previous reconstructed sample plus the difference this is 2, sorry, this is 2. So, this is equal to x1 plus q1 and dq2 is d2 plus q2. Now, from this we get this is equal to x2 plus q1 plus q2. So, if we continue this process and try to find out all the reconstructed samples, what we would get is something like this. Dn is obtained like this. My dqn is equal to Tn plus Qn, and my reconstructed sample at the receiver would be equal to So, there is an interesting thing we have got. We see that this is the quantization error which occurs in the reconstruction of the nth sample of the sequence, the original sequence xn. So, this quantization error accumulates as the process continues. Now, theoretically, if the quantization error process is a zero mean process, then the errors will cancel each other in the long run. But in practice, often long before that can happen, the finite precision of the machine causes the reconstruction value to overflow. So, why is this happening? It is important to note that the encoder at the transmitter end and the decoder, that is the reconstruction at the receiver end, are operating with different pieces of information. The encoder generates the different sequence based on the original sampled values, while the decoder adds back the quantized difference onto a distorted version of the original signal. Correct? So, now this problem can be solved by forcing both the encoder and decoder to use the same information during the differencing and reconstruction operation. Now, remember, the only operation available at the receiver about the sequence xn is the reconstructed sequence xqn. Now, as this information is also available at the transmitter end, we can modify this differentiating operation to use the reconstructed value of the previous sample instead of using the previous sample itself. That is, what we will do is that we can obtain Dn as xn minus xq n minus 1. So, let us see if we follow this strategy what would happen. So, I have at the receiver this block. Now, what I am saying is that since this reconstruction can also be done at the transmitting end, because it is using for reconstruction at the receiver end only the different sequence, and which is also available at the transmitting end. So, this block, this red block which I have marked in dotted, can be put at the transmitting end itself. Now if we do this, let us see what are we going to get. So now my D1 is going to be x1 minus x0. Again I assume that x0 is known to the receiver, it could be assumed to be 0. Now this is going to be quantized, so I will get as a quantization noise. So your reconstructed value at the receiver would be this. This is known at the receiver. So the quantization error which I get for the first sample is the same as I got in the earlier case. Now let us look for the second difference sample. Now here I use the current sample and I use the previously reconstructed sample, and then I pass it through a quantizer. Now I reconstruct at the receiver as follows: my previously reconstructed value plus my received difference signal. This I can rewrite it as and from here you can see that this is nothing but x2 plus q2. Interesting. I get only one term out here which is going to bring about the distortion in the reconstruction of the second sample, unlike the previous case where I had q1 also. Now if I proceed in this manner, what I will get is as follows: my dn would be given by this expression. This will get quantized, and my reconstruction at the receiver would be as follows. I take my previously reconstructed value, to that I add the current difference sample, which I can rewrite it as now this plus this is nothing but equal to xn plus qn. So at the nth iteration there is no accumulation of the quantization noise. In fact, the quantization noise in the reconstructed sequence is the quantization noise incurred by the quantization of the nth difference. So the quantization error for the difference sequence is substantially less than the quantization error for the original sequence. Therefore, this procedure will lead to the overall reduction of the quantization error. So what we could say that if we are satisfied with the quantization error for given number of bits per sample, then we can use fewer bits with a differential encoding procedure to obtain the same distortion. Now in our discussion so far, what we have said is that we are using this kind of differential encoding scheme. So, in this scheme, we would like this dn to be as small as possible, correct. What this implies that this xq should be as close as possible to this x. However, this xq is the reconstructed value of x n minus 1, correct. So, what we would like that this xq should be very close to xn minus 1. Now, unless this xn minus 1 is very close to xn, some past values of the reconstructed sequence can often provide a better prediction of this xn. So, let us modify this figure to replace the delay with a block called a predictor block, and we will get this figure as shown here. Now, this P out here, predictor block, is nothing but a function of the reconstructed past values and this let us call as x hat n. So, this is the predictor which is obtained as a function of this reconstructed past value. So, this basic differential encoding system is known as differential pulse code modulation. In short, DPCM. So, this DPCM consists of two blocks, one is the predictor block and the other is the quantizer block. We will study the predictor block and the quantizer block design and see how they function in a differential encoding system, and that we will do next time. Thank you.